Okay, so now let's talk about the work energy theorem. This is probably one of the most important conceptual ideas from this chapter. The work energy theorem explains why we defined work in the first place. So we previously defined work both with the differential form and the integral form, and we have these somewhat messy equations, but we learned how to solve these and to calculate the work. But why did we bother doing this? Well, we see work and force are related, and with the work energy theorem, we're going to relate work and energy. And in doing so, since force is related to work and work is related to energy, we're going to be able to connect the concepts of force and energy. And in doing so, we're going to make some problems much easier to solve. Okay, so let's go through this. We're going to derive the work energy theorem in just one dimension, and that'll be something we can expand to use in 3 dimensions. So let's start with our general equation for work in one dimension. So it's the integral of force as a function of distance traveled. Okay, that's our general equation for one dimension. Um, Force is equal to mass times acceleration. So I'll rewrite force in terms of mass times acceleration and plug that into our integral. And mass is a constant, so I'll just pull that out of the integral. Okay, now let's do a little fancy trick. We know acceleration is the derivative of velocity with respect to time, right, dv dt. And so let's use a chain rule. We could rewrite dv dt as dv dx dx dt. Okay, we're free to do that. And so we can note dx dt is equal to velocity, right? So I can rewrite acceleration as velocity times the derivative of velocity with respect to position. Okay, and so I can take the work equation we had written previously, and I can replace acceleration with velocity times dv dx, which we've done here. The dx's cancel, and I get v dv. Okay, now instead of an integral over x, I'm integrating over velocity. This is an easy integral to do, where I'm just integrating velocity with respect to velocity from v1 to v2 between two different velocities. And so integral of v is 1/2 v squared. So I get 1/2 mv squared evaluated from v1 to v2. So I get 1/2 mass times my final velocity squared minus 1/2 my mass times my initial velocity squared. Okay, so this, it turns out we can rewrite the work in terms of this quantity, subtracting these two velocity squared terms. Okay, and so we have this rewritten equation for work, and we see this 1/2 mv squared keeps popping up. So let's give that a name. We're going to call it kinetic energy. Kinetic energy is defined to be 1/2 mass times velocity squared. Okay, um, and so this is kinetic energy at time 2. This is kinetic energy at time 1. So I can rewrite my work in terms of work is equal to my final kinetic energy minus my initial kinetic energy. So the total work done on an object is equal to the change in the kinetic energy of that object. And this is our work energy theorem. And this is important. If we're doing a net positive work on an object, we're going to have a positive change in our kinetic energy. That means K2 is bigger than K1, which means our kinetic energy is increasing. The object is speeding up. Right? Kinetic energy depends on your speed squared. Right? So if your kinetic energy is increasing, your speed is increasing. If I'm doing negative total work, this is going to be negative. My kinetic energy is going to be decreasing. And if I'm doing zero total work, my kinetic energy is not going to change. Right? So that's the work energy theorem. It's going to allow us to solve a lot of problems. Okay. A little bit more about kinetic energy. Kinetic energy is a scalar quantity, right? It's a number, not a vector, and that's a really good thing because scalars are easy to work with. We don't have to deal with unit vectors and keeping x, y, and z separate. It's just a number. We can see that if our speed is 0, if our object is at rest, v is 0, and kinetic energy is 0 in that case. We can also see that it's always positive. It doesn't matter if your velocity is positive or negative. We're squaring it, right? So this is always going to be a positive number. And finally, we can check the units of kinetic energy. It's mass, which is kilograms, times velocity squared, meters per second squared. And this is exactly our definition of what a joule is. So kinetic energy and work have the same units, and that's equal to a joule, right? They better have the same units, because work is equal to the change in kinetic energy. Both of these are measured in joules, right? So that's kinetic energy. And now we have the work energy theorem. The work done by the net force of an object, net force on an object, equals a change in the object's kinetic energy. Right? That's the work energy theorem. we have a net force that has some alignment with the displacement direction or anti-alignment with the displacement direction, we're going to do work, and that work is going to be used to increase or decrease the kinetic energy of our object. As we mentioned, if the total work is positive, if this is positive, the kinetic energy must increase, object must speed up. If the total work is negative, the object will have a decrease in kinetic energy, the object will slow down. Another way of saying this is if the kinetic energy of an object is equal to the total amount of work needed to accelerate the object from rest to its present speed. Right? So if the object is at rest, k1 is 0, the kinetic energy at time 1 is equal to 0. And so in that case, the kinetic energy at the final time is just equal to the work done on the object. So the kinetic energy is equal to the work done on that object to get it up to its current speed. Likewise, kinetic energy is the total amount of work it takes to bring a particle to rest. So if you have an object that has some kinetic energy, it's moving really fast, the kinetic energy is equal to the work it takes to bring that object to a rest. So it's another way of thinking about what is kinetic energy. And as we mentioned, this is going to be really useful to solving problems, and we're going to do a lot of problems in the next few chapters using this concept, and we're not going to have to use vectors, so that's wonderful. So what's a summary? What's the big idea about work and energy? A force applied over some distance gives rise to work. If the force is aligned with the displacement, it'll be positive work. If the force is opposite the direction of the displacement, it'll be negative work. If the force is perpendicular to the displacement, it'll be 0 work. We can add up the work done by all of the forces acting on an object to define the net work or the total work done on that object. If the net work or the total work is positive, the kinetic energy of that object will increase by the work energy theorem. If the total work is negative, the object will slow down. The kinetic energy will decrease. Okay, so that's the big idea here, and we'll use this to solve some problems in future videos.